Hello friends, this video on alcohol, phenol and ether part 22 is brought to you by examfear.com. No more fear from exam. Let's understand some chemical properties of phenols. We'll understand some reactions for phenol. We'll talk about electrophilic aromatic substitution for phenol. We'll talk about halogenation, sulfonation, nitration. We'll talk about Cope's reaction. We'll talk about Riemann-Tiemann reaction. We'll talk about the reaction of phenol with zinc dust, reaction of phenol with ammonia, reaction with acid chloride, reaction with haloalkanes, reaction with nitric acid. We'll talk about oxidation, we'll talk about dehydrogenation, and we'll also talk about acidity of phenol. So before we start this reaction, let's understand one thing. So in phenol, I have this OH group. And this OH group is nothing but electron donating group. And since this donates electron, right? So this whole phenol is more prone to electrophilic substitution reaction. Why electrophilic? Because it has more electrons here. If you see, right, more electrons in these things, and generally in ortho and para position. Why? If you draw a resonance structure, you'll see that the ortho and para position, this has more negative charge. Right? Thus, phenols activates the ring towards electrophilic substitution reaction. If you see, we'll study so many electrophilic substitution reaction here. Please note that when you have OH attached to aliphatic hydrocarbon, so in that case, this oxygen is an electron withdrawing group because the difference in electronegativity. Right? So it withdraws electron. But when it is attached to a aromatic hydrocarbon, it is electron giving group, correct? Or electron donating group. Why? Because it has lone pair. So please keep this difference in mind. The same OH, when it is part of aromatic ring, it gives electron. When it is part of aliphatic hydrocarbon, it withdraws the electron. This is because of lone pair, and this is because of electronegativity difference. So let's see the nitration reaction now. So if you see the reaction, I have this phenol. React with nitric acid in presence of some sulfuric acid. I'll tell you why sulfuric acid is required. You get ortho and para nitrophenol, and this can easily be separated. Why? See, because this guy has intermolecular hydrogen bonding, the boiling point is high, right? This has intermolecular, the boiling point is less, so you can easily separate them by steam distillation because they have different boiling points, correct? Let's see the reaction mechanism here. So as I told, you first have nitric acid. It reacts with H plus. What you get is NO2 plus and water. Correct? So this NO2 plus is like this. And this is the one that reacts. So let's see the reaction. I have this phenol here. See, this is my phenol, and I have NO2 plus, correct? This is a bond here. It is electron rich bond, and this is electron deficient nitrogen. So this bond will break and link with this guy, and this is a hydrogen obviously already there, correct? So with this, what will happen is this bond will break actually in this fashion, correct? Minus and plus. So what you get here is something like this. You get NO2, the charge will go off from nitrogen because positive and negative will form a bond. Here you get a positive charge, and here is already H here. Now the aromaticity is broken. And we don't told that aromaticity brings stability, so we want the aromaticity to be back. So for that, this hydrogen will say, okay, I'll go off. So what this guy will do is, this will go off, this bond will break into plus and minus, right? This will become minus, this will become plus, plus H will go off, and this minus and plus will again form a bond. Correct? This is NO2 and you will form a bond here. Sorry, this, yeah. And this is what you get. The same thing, the NO2 can attack at this position and at this position. Why? We have seen that why this, I can show you that. You see this OH minus, right? So this is ortho and para diatribe. I'll not explain this. I think I have explained this so many times that this is ortho and para diatribe group. With ortho and para position, if you talk about resonance structure, it will have more negative charge. Okay, let me draw it actually. If the students has not seen, just for the convenience. So I have OH, and let me suppose this is my bond, and this is a lone pair of electron. It will give the electrons to this benzene ring. So what will happen is, in this case, it will form a double bond, right? Since it has given electron, it will get a positive charge. Now this bond will break this bond, so I get a negative charge here. Correct? So electrons move from here to here, it gets negative charge here. Again, you can draw more resonance structure. So here also, if you see this electron, if it moves in this direction, negative and positive will form a bond here, negative charge will come here. Let's see this. So this you get OH plus 2, here you get bond, here you get negative charge. Again, what you can do is, this electron will move in this direction, negative charge, here positive charge, positive and negative will form a bond. Right? And again, the next thing will be, it goes back actually in this direction, and it goes back to this shape. So this is the resonance structure I have, and if you see here, I have ortho and para position, I have more electron density, and thus NO2 plus, since it is plus, it will attack at these positions. Hope you understand, and that's why you get ortho and para output. So the next is halogenation. So halogenation is also similar to nitration. So I have OH here, you add Br2 in presence of FeBr3. So what you get is OH and Br. Same ortho and para position. Why? Because OH group directs this Br plus to ortho and para position. Correct? Let's see the reaction mechanism for this. See, the first thing happens is Br, right? When it reacts with FeBr3, what you get is Br plus, sorry, this is plus actually, and FeBr3 minus. That's what you get, right? Now what happens is, this is plus charge. Now it is easily attacked by this. See, this OH, this is my phenol here, and if I get this Br plus here, FeBr. So let's see this reaction now. This is a lot of electrons here. This will attack this guy. So what will happen is, here this is H already. So this will break in this format, because we saw that in the resonance structure it has negative charge here, right? So with this, what we'll get here is OH, this bond will break, you'll get a positive charge here, and H here, and Br here. Correct? Now since the aromaticity is broken, we want to return it back. So this hydrogen will say, okay, I'll go off from here. So this hydrogen bond will break, right? So it will get a negative charge here, negative and positive will form a bond here. Correct? And this is the fast one. This is slow actually, and this is fast. Same thing will happen at para position also. The next reaction is sulfonation reaction. Before I move to sulfonation reaction, let me tell you one thing. In the same bromine water, right? The same phenol. If you put excess bromine water, so what will happen is you'll get something like this. Here at ortho and para position, all the hydrogen will be replaced by Br. Correct? Now let's start with sulfonation. So for sulfonation, the reaction is pretty simple here also. Similar pattern, I have OH, then I have H2SO4. This gives me this OH. Here you get SO3H at ortho position, or you get SO3H at para position. Correct? So we'll see the reaction mechanism for this. See, for H2SO4, the one that is involved in the reaction is this guy, SO3. Correct? And this is electron deficient. So what happens here is, let's see the reaction mechanism here. OH, I have SO3. This is electron deficient, so this guy will say, okay, let me break my bond. I get a negative charge here, right? And then let me form a bond like here, this here. So with this, and already there was a H here, so I'll just put the H. So what you get with this is, this bond is broken. This is broken into negative and positive. This is positive here, right? And this side you have H, and then you have S O minus. That is what you will get. Correct? Now this broke the aromaticity, so I don't want to break this. So this hydrogen will say, okay, I'll go out of this. So it will go out in this fashion, right? This becomes H plus, and this plus and minus will form a bond here. And this hydrogen, when it comes out, right, it will attack this one. So what you get here is, in this step, so this bond is formed again, and you got this O minus will get hydrogen H plus, it will get H plus. So you form this compound, and aromaticity is back. Thank you. Visit our website examfear.com to watch more and more quality education videos. You can also attempt free online tests that are there in our website. You can also get access to tons of free study materials, and you can also find free tutors and mentors in this website. Thanks a lot for watching.